Welcome back to the CCSP Exam Cram Series 2023 edition, in this installment covering every topic in the official exam syllabus for Domain 4 of the CCSP exam. As a cybersecurity strategist and a VCSO for a regional bank, cloud security is a core part of my day-to-day role, and I do find the skills measured in the CCSP exam to be very relevant for today's cloud security professional. Last year, I helped hundreds of thousands achieve cybersecurity certifications, like the Security Plus, the CISSP, and now bringing that formula to the CCSP exam, helping you get ready for exam day without the need for expensive boot camps. In the series, we'll have 6 installments, one for each domain of the CCSP exam. Today, we're on installment number 4, focused on Domain 4. When the series wraps, I'll consolidate these into a full course video. The focus in Domain 4 is Cloud Application Security. As always, I recommend the CCSP Official Exam Study Guide and Practice Test Bundle to use as part of my exam preparation strategy to get ready for exam day. It includes 1,000 practice questions, 2 practice exams, and some flashcards to help you review. And you can find a link to the latest and least expensive copy on Amazon.com in the video description. As always, I'll provide a downloadable PDF copy of this presentation, also linked in the video description. And also in the video description, you'll find a clickable table of contents allowing you to move forward and back through the video as necessary during your exam preparation. And with that in mind, let's get started with Domain 4, Cloud Application Security. So let's take a look at the exam essentials, those areas the official study guide advises will factor prominently on exam day, beginning with cloud development basics, pitfalls, and vulnerabilities. So here we'll talk about performance, scalability, portability, and interoperability as they pertain to cloud, as well as the popular threat lists from OWASP and SANS. Up next, we'll talk about the application of the software development lifecycle, or as you'll hear it referred to in the CCSP context, the secure software development lifecycle. We'll touch on development models like Agile and Waterfall, threat models, as well as secure coding practices and standards. Then, applying test methodologies to application software. We'll touch on functional and non-functional testing, static and dynamic testing, as well as the QA process. We'll touch on managing software supply chain security and secure software usage practices. Common application security technology and security controls. We'll look at elements of design and data encryption, as well as orchestration and virtualization. And finally, identity and access management solutions, as well as common threats to identity and access. We'll start with 4.1, advocate training and awareness for application security. And here we'll drill down on cloud development basics, common pitfalls, and common cloud vulnerabilities with some focus on the OWASP Top 10 and SANS Top 25 lists. We'll start with cloud development basics, and we see 3 key concepts called out in the official study guide. There is security by design, which declares security should be present throughout every step of the process. And various models exist to help, like the building security and maturity model. This pairs well with DevSecOps. Then there's shared security responsibility, the idea that security is the responsibility of everyone, from the most junior member of the team to senior management. That describes the primary principle of DevSecOps, where security is present throughout the software development lifecycle and everyone is responsible for security. And finally, we have security as a business objective, where risk mitigation through security control should be a key business objective similar to customer satisfaction or revenue. This does require organization-wide security awareness and commitment in order to be effective. Common pitfalls of application security in the cloud. So we'll touch on performance, scalability, interoperability, portability, and API security. You'll want to know the common pitfalls and the advantages of avoiding each of these. So we'll start with performance. So cloud software development often relies on loosely coupled services. This makes designing for and meeting performance goals more complex, as multiple components may interact in unexpected ways. You want to verify functionality and performance through end-to-end load and stress testing. And we have scalability. One of the key features of the cloud is the ability to scale, allowing applications and services to grow and shrink as demand fluctuates. It does require developers to think about how to retain state across instances and handle fault with individual servers. Scale out tends to be better than scale up in the cloud. We can scale out with additional instances to meet demand and scale back during times of lesser demand, and our overall run rate is going to be less than deploying a smaller number of larger instances that run, billing us all the time for unused capacity. Next, we have interoperability. This is the ability to work across platforms, services, or systems, and can be very important, especially in multi-vendor and multi-cloud scenarios. Interoperability across platforms increases service provider choice and can ultimately reduce costs. Then we have portability, designing software that can move between on-premises and cloud environments or between cloud providers. That's what makes it portable. Portability in a hybrid scenario requires avoiding use of certain environment or provider-specific APIs and tools. That additional effort can make it harder to leverage some cloud advantages, and it may require some compromises. Because not all tools we use on-premises may translate to the cloud, and certainly not all the features in the cloud are going to be available back on-premises. And finally, API security. So application programming interfaces, or APIs, are relied on throughout cloud application design, development, and operation. And designing APIs to work well with cloud architectures while remaining secure are both common challenges for developers and architects. Our API considerations need to include access control, data encryption, throttling, rate limiting. Your CSPs offer PaaS services that simplify addressing API concerns. And you'll find the CSP offerings also address the need to present your APIs in multiple regions and multiple geographies. So let's talk for a moment about cloud vulnerabilities, common cloud vulnerabilities. There are several groups that provide guidance on common application vulnerabilities and related security threats. So in terms of vulnerabilities, we're talking about common cloud vulnerabilities to avoid within the secure software development lifecycle. These include data breaches, data integrity issues, insecure application programming interfaces, and denial of service. And there are organizations that provide information on security threats. The Cloud Security Alliance, the SANS Institute, and the Open Web Application Security Project, or OWASP. And later in this domain, we will dive into some of the top security concerns and risks as identified by some of these organizations. Next up is 4.2, describe the secure software development lifecycle process. Here we'll focus on business requirements, as well as phases and methodologies. We'll touch on the phases of the secure software development lifecycle, as well as waterfall and agile methodologies for managing software development efforts. So first we have business requirements. So mature software development shops utilize a secure software development lifecycle because it saves money and it supports repeatable quality software development. The secure software development lifecycle is fully successful only if integration of security into the organization's existing software development lifecycle is required for all development efforts. It must be mandatory. We have business requirements that capture what the organization needs its information systems to do, and then we have functional requirements which detail what the solution must do, such as supporting max concurrent user requirements, which then turn into business requirements like supporting all workers being able to access a system to perform their assigned duties. In addition to these functional requirements, the organization must also consider security, privacy, and compliance objectives and requirements. So when regulatory requirements are involved, objectives become requirements in a hurry. Moving on to the secure software development lifecycle, if we take a look at the common phases of a typical lifecycle, we have planning that leads to requirements, and then a design, and then coding that design, and then testing, and then ongoing care and feeding, which we call maintenance. These are the common phases of the secure software development lifecycle. Now, there are multiple variations of the secure software development lifecycle. I did want to just briefly mention that if you see the acronym SSDLC, that's just another way of saying Secure Software Development Lifecycle, and I saw that acronym called out in the common body of knowledge. Now, regardless of which SDLC model a company uses, there are a few phases that appear in all models: planning, requirements definition, design, and coding. These are mentioned in the official study guide, so ensure you're familiar. We have planning, which considers potential development work, focusing on determining need, feasibility, and cost. Do we need it, and is it possible for a reasonable cost? Requirements definition. So once an effort has been deemed feasible, user and business functionality requirements are captured. This involves user, customer, and stakeholder input to determine desired functionality, identify current system or app functionality, and the desired improvement. And then the design phase focuses on designing functionality, architecture, integration points and techniques, data flows, and business processes. The solution is designed based on requirements that we gathered in the requirements definition. And then in the coding phase, this is where the actual coding, the work, happens. Now, the CCSP exam outline mentions 4 phases in a secure software development lifecycle, or at least it calls out these 4 phases of the lifecycle, and those phases are design, code, test, and maintain. So these are mentioned in the official study guide, so make sure you're familiar. We have the design phase. Again, the solution is designed based on requirements gathered. Code, this is where the coding work, the real work happens. Then the test phase, this is testing to ensure software is functional, scalable, and secure. And then maintain, ongoing maintenance updates, patching, and checks to ensure software remains functional and secure. Now, there are only 2 software development models called out in the official exam syllabus, and only 2 likely to appear, and the first is Agile, which places an emphasis on the needs of the customer and quickly developing new functionality that meets those needs in an iterative fashion, through iterations. And then there's the waterfall model, which describes a sequential development process that results in the development of a finished product. So Agile is defined by its ability to allow quick response to changing requirements and rapid iterations of prototypes, where waterfall requires clear requirements, a stable environment, and a low rate of change. The waterfall model has 7 phases, 7 stages. There's system requirements, software requirements, preliminary design, detailed design, code and debug, testing, and operations and maintenance. So these phases happen in sequence, and the waterfall model only allows returning one phase back for correction. So it's a bit inflexible, much like we cannot change the direction of a waterfall. The waterfall model does not allow us to easily pivot to new directions. As a result, the waterfall model has declined in popularity in recent years. It is relatively uncommon in cloud development, and it's seen as legacy by many. The Agile model for software development is based on the following 4 principles: individuals and interactions over processes and tools, working software over comprehensive documentation, customer collaboration over contract negotiation, and responding to change over following a plan. Agile was first described in the Manifesto for Agile Software Development back in 2001, and it leverages an iterative, a repeating process called a sprint. So we have sprint planning, development, testing, demonstration, and then we repeat that through iterative sprints. We plan our work, we do the development work, the coding, we test, we demonstrate, we have a demo day at the end of every sprint, and then we do it over and again. And a standard sprint is 2 weeks. You'll see some organizations that'll run 1-week sprints. And a small project might be something you can complete in a single sprint. You may have large projects that take many sprints over a period of months, but we'll repeat that process from the first sprint to sprint N, however many that is, to the end of our project, at which point we have a working piece of software. Up next in 4.3, apply the secure software development lifecycle. Here we'll touch on cloud-specific risks, threat modeling, avoiding common vulnerabilities during the development process, secure coding, and we'll focus on some specific secure coding standards that are expected to appear on the exam, and software configuration management and versioning. So cloud-specific risks are called out in section 4.3 and are actually revisiting a concept we covered previously. These were covered in Domain 3. They come straight from the CSA website. This is the CSA Egregious 11, and they're covered in depth in the Common Body of Knowledge as well. So in Domain 3, we covered them from an architecture perspective. Here, we will cover them briefly from a software development lifecycle or secure software development lifecycle perspective in the context of DevSecOps and continuous integration and continuous delivery. We have data breaches, loss of sensitive data due to a security breach, and from a development perspective, we'd want to implement centralized secrets management using a Vault solution in the cloud, which all the major CSPs offer, data masking to obscure visibility of sensitive data at the database tier, even from our database administrator. So we can leverage a solution like data masking to allow our database administrator to manage the data without being able to fully see sensitive data. And then misconfiguration and inadequate change control. And here is where CI/CD and infrastructure as code come into play. We define our application infrastructure in code. We deploy it hands-free through a CI/CD process, through a pipeline to eliminate human error. And we implement release management, so we have human approval gates. We have checkpoints to make sure that a smart person in the chair with the right training verifies that the code we're about to release has in fact gone through all the appropriate validation procedures. It's gone through testing and QA, and we know that code is functional and secure before we release it into production. And then there's lack of cloud security architecture and strategy. We really need to implement security from the design phase, and we need to remember our obligations in the shared responsibility model. So whether we're implementing an IaaS or PaaS or leveraging a SaaS service, remembering where our security responsibilities begin and end. And insufficient identity, credential access, and key management. So we're really talking about identity and access management here, identity providers. And a great solution here is developers can leverage identity as a service rather than building their own, resulting in stronger authentication and authorization controls quite typically, and certainly a more mature approach. And in this case, it's really about making good decisions as to where we want to innovate and where we want to leverage existing solutions that come in the cloud. Account hijacking, credential theft, abuse, or elevation to carry out an attack. Again, using existing identity providers, identity as a service for your app reduces risk. Insider threats. Here we leverage separation of duties, checks and balances in the release management process like those approval gates I just mentioned. Insecure interfaces and APIs, so failing to secure our APIs. We implement access controls like role-based access control, and for our APIs, we'd implement access keys, API keys. And a weak control plane, weaknesses in the elements of a cloud system that enable the environment configuration and management. Here, continuous integration and continuous deployment. We're not deploying through the web console or from the command line. It's codified, automated, and deployed through a pipeline. And that brings us to threat modeling, which allows security practitioners to identify potential threats and security vulnerabilities. It's generally used as an input to risk management. And it can be proactive or reactive, but in either case, the goal of threat modeling is to eliminate or reduce threats. There are three approaches to threat modeling, three common approaches, I'll call it. There's the asset focus, which uses asset valuation results to identify threats to the valuable assets. That's where we want to focus our effort. We're focused on attackers, identifying potential attackers and identifying threats based on the attacker's goals. Or focused on software, considering potential threats against software the organization develops. So either assets, attackers, or software. So now let's look at some common threat modeling approaches. First, we have STRIDE, which was developed by Microsoft, and it stands for spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. So going back to the three approaches, it's focused on potential threats against software the organization develops. Then we have the DREAD model, which is based on the answer to 5 questions. What is the damage potential? The reproducibility, exploitability, affected users, and discoverability. So DREAD is looking more from an attacker's perspective. What is the potential damage? Can it be reproduced? Is it a vulnerability that can be exploited? And who would our effective users be? What would the scope of the exploit be? And how discoverable is the vulnerability? If it can't be discovered, it can't be exploited, and therefore we'll worry less about it. Next up, we have the PASTA model, which focuses on developing countermeasures based on asset value, the third of those three approaches to threat modeling. PASTA involves 7 stages. We have definition of objectives, then definition of the technical scope, app decomposition and analysis, Stage 4, threat analysis, Stage 5, weakness and vulnerability analysis, Stage 6, attack modeling and simulation, and Stage 7, risk analysis and management. So PASTA will bring us to answers to many of the same questions we saw in DREAD: damage potential, exploitability, discoverability, just coming at it from a different angle. And finally, we have ATASM, and this acronym stands for architecture. So the process begins with analysis of the system's architecture. This is followed by an examination of threats, listing all possible threats, threat actors, and their goals. And then examining attack surfaces, identifying components that are exposed to attacks. And finally, mitigations, analyzing the existing mitigations in place, those security controls already protecting the system, to determine if they are indeed adequate. Now, the thing about ATASM is it's not actually a threat model itself. It's a series of process steps for performing threat modeling. And because it is not actually a threat model itself, it can be used with threat models like STRIDE, DREAD, and PASTA. It's some really common sense thinking. Now we're going to talk a bit about how to avoid common cloud vulnerabilities. And like all risk mitigations, a layered approach combining multiple types of controls is a best practice, including training and awareness of our developers, which is critical because they make decisions about how to design and implement system components. Awareness of common flaws like injection attacks, for example, prevent coding mistakes. And in the next section, when we talk about secure coding, we'll take a look at some artifacts from organizations like OWASP and SANS that can help us in training our developers around awareness of those common flaws. Documented process. Secure SDLC should be well documented and communicated to all team members designing, developing, and operating systems. It's similar to security policies, and it has to be understood and followed by our developers. Test-driven development, focusing on meeting acceptance criteria, can be one way of simplifying the task of ensuring that security requirements are met. Having well-defined test cases for security requirements can help avoid vulnerabilities like OWASP Top 10 application security risks. This ensures developers know what tests will be conducted against their code. And common cloud vulnerabilities are well known, and they're documented in lists like the OWASP Top 10 list and the CSA Egregious 11. And we can use these to build our well-defined test cases. These documented vulnerabilities can guide what we're testing against and testing for. Let's shift gears and talk about secure coding. So this is the practice of designing systems and software to avoid security risks. It's essentially a proactive risk mitigation practice. We are, through secure coding, avoiding potential security risks. And there are multiple organizations out there that exist and work to mature secure coding practices. The syllabus calls out 3 of these. OWASP, which produces the Cloud Native Application Security Top 10 list, and their better known and older Top 10 Web Application Security Risks. The exam also mentions the SANS Top 25 as well as Safe Code standards, and we'll touch on all of these. So let's start with the OWASP Top 10 Web Application Security Risks, which is an awareness document that represents a broad consensus about the most critical security risks to web applications. So quickly running through these 10 in order, we have broken access control, cryptographic failures, injection, insecure design, security misconfiguration. You'll notice that some of these are really self-explanatory. Vulnerable and outdated components, identification and authentication failures, software and data integrity failures, security logging and monitoring failures, and server-side request forgery, which is a pretty common, or at least a well-known attack. 2 things about this list. Number 1, it changes from year to year, so you'll see these risks moving up and down the list or potentially off the list as they become less common. For example, server-side request forgery was higher up this list 5 years ago. For the exam, be familiar with the meaning around these concepts. Don't worry about memorizing these specific items or their order. Now let's move on to OWASP Cloud Native Application Security Top 10. The primary goal of this draft is to provide assistance and education for organizations looking to adopt cloud-native applications securely. And in this top 10, we have insecure cloud container and orchestration configuration, injection flaws, improper authentication and authorization, CI/CD pipeline and software supply chain flaws, insecure secret storage, over-permissive or insecure network policies. So you'll notice again many of these are self-explanatory. Using components with known vulnerabilities, improper assets management, inadequate compute resource quota limits, and ineffective logging and monitoring. And for the exam, you want to be familiar with the common solutions around these problems and best practices, which are all covered in this series. So there's really not any real additional reading that you need to worry about here. So moving on to the SANS Top 25 Most Dangerous Software Errors. This list is not specific to cloud-native environments like the OWASP Cloud-Native App Security Draft we just looked at. And because it's not specific to cloud-native environments, it seems to get a bit less attention in the official study guide and in the common body of knowledge. But we're going to cover it anyway for reasons that'll be apparent in a moment. You're going to see some patterns developing here across these various standards. So going through the top 25, these do change from year to year in this list. And for the exam, you'll want to know the attack types. Don't memorize this list. It's an even longer list. Don't memorize the list, but I'm going to call out the attack types for you here, and we'll cover those at the end. So when we get to the end of all of these mini lists, you'll be ready for exam day. So from number 1 to number 25, we have out-of-bounds write, which is a type of buffer overflow attack. There's an improper neutralization of input, a cross-site scripting attack. Number 3 is a SQL injection. Number 4, improper input validation. Input validation actually prevents injection attacks. If I validate the input to a form, it prevents a SQL injection, for example. Out-of-bounds read is another buffer overflow type attack. Improper neutralization of special elements, that's an operating system command injection, so another injection attack. Use after free, another buffer overflow type attack. Improper limitation of a path name, that's a path or directory traversal we'd call it. Now this SANS Top 25 list uses the Common Weaknesses Scoring System, or CWSS. by the by. So continuing down the list here, number 9, cross-site request forgery. Pretty widely explained attack, less common than it used to be. Unrestricted upload of file with dangerous type. Null pointer reference. Deserialization of untrusted data on number 12. Number 13 is integer overflow or wraparound. What I will tell you about numbers 11 through 13 is input validation of various sorts will fix all 3 of these. The type of input you're validating varies, but input validation is helpful in all of these. Number 14, improper authentication. Number 15, use of hard-coded credentials. Then missing authorization. Then improper neutralization of special elements, another injection attack, and then rounding out this page, missing authentication for critical functions. So you'll notice authentication and authorization as a theme surfacing here, so knowing the best practices there will be important. Now that CWSS, that scoring system, is actually composed of 3 scores, I should mention. There's the base finding score, the environmental score, and the attack surface score. I'm not sure the exam's going to get that deep, but I wanted to call those out just so you have them top of mind. And finishing out the top 25 list, we have improper restriction of operations within the bounds of a memory buffer. That's another buffer overflow attack. Incorrect default permissions, so identity and access related, let's call it. Server-side request forgery, another fairly well-known attack, less common than it used to be. That's actually on the OWASP list, you may remember. Concurrent execution of shared resource with improper synchronization, a race condition this is called, another type of attack you should be familiar with. Number 23, uncontrolled resource consumption. So this would be a denial of service attack. Improper restriction of XML external entity reference. So number 24 isn't a directory traversal attack, but it does result in some unauthorized local file access, basically. And number 25 on the list, improper control of generation of code, another injection type attack. So I want to just recount for you some attack types and concepts here, some themes if you will. So we have injection attacks, buffer overflow attacks, directory or path traversal, denial of service or distributed denial of service, race condition, and then authentication and authorization. So an understanding of the attack types should be enough for exam day, and you saw these themes across all of these lists to varying degrees. The authentication and authorization is really more a matter of knowing best practices, and we're going to touch on authentication and authorization from multiple directions in this course and in this series, so I don't think you have much to worry about there. But what I would like to do is, just in case you're not familiar with these types of attacks, I'm going to just walk you through a simple explanation of numbers 1 through 5, so in case you haven't been exposed to these in your work life, you'll have a good foundational knowledge. So let's start with injection attacks. Improper input handling is really the source cause here. These are used to compromise web front-end and back-end databases. SQL injection is the most widely known. That's where the attacker uses unexpected input to a web application to gain unauthorized access to an underlying database. It's not new. It can be prevented through good code practices. Essentially, the countermeasure is input validation and using prepared statements like stored procedures rather than allowing SQL queries to be generated from that front-end web application. We don't allow the front-end web application to issue select statements. Instead, we limit that front-end web application to calling stored procedures, which are pre-compiled and allow us better control. But input validation is the key. Now, another I mentioned was buffer overflows. These are attacks used to exploit poorly written software. This exists when a developer does not validate user input to ensure that it's an appropriate size. For example, it allows an input that is too large to overflow a memory buffer. But you see a theme here, right? We can prevent this with input validation. Another attack type is directory traversal we saw on the list, gaining access to restricted directories. If an attacker can gain access to restricted directories through HTTP, that's what we call a directory traversal or path traversal attack. One of the simplest ways to perform directory traversal is by using a command injection attack that carries out the action. And if successful, it may allow the attacker to get to the site's root directory. Most vulnerability scanners will check for weaknesses with directory traversal or command injection and inform you of their presence. So, to secure your system, you should run a vulnerability scanner and keep the web server software patched. It's as simple as that. Another type of attack we saw called out in the list was a resource consumption attack or a denial of service. There's denial of service, which is a resource consumption attack intended to prevent legitimate activity on a victimized system. It essentially consumes all of the processing and memory resources on that system. There's a distributed denial of service attack, or DDoS, and that's a DOS attack utilizing multiple compromised systems as sources of attack. The distinction here is the distributed denial of service, or DDoS, involves multiple systems, where denial of service may involve just a single system. Your countermeasures here are several. Good firewalls, routers, intrusion prevention systems, security information event management so we can identify malicious activity more quickly across our estate, disabling broadcast packets entering and leaving our trusted network, disabling echo replies, the ping echo or ICMP echo reply, and keeping our systems patched. So many of these attacks exploit known vulnerabilities that just patching systems goes a long way. But denial of service and distributed denial of service represent a class of attacks. These aren't specific attacks. There are many variations of denial of service and distributed denial of service, so we call these a class of attacks. And we've already discussed in this series how CSPs provide some built-in protections or some premium tier capabilities to protect against distributed denial of service attacks. We're really approaching it from a more fundamental perspective here, as some of those lists amongst OWASP and SANS are not specific to cloud computing, and certainly in a hybrid cloud scenario, one would want to know how to protect against these sorts of attacks. Now, the last attack type I want to cover with you is the race condition. This is where the system's behavior is dependent upon the sequence or timing of other uncontrollable events. A common race condition is the time of check to time of use condition. This is a timing vulnerability that occurs when a program checks access permissions too far in advance of a resource request. The problem occurs when the state of the resource changes between the time the application checks the state of the resource and the time the application or service attempts to use that resource. A great example is file locking. The application checks the file to ensure it's not locked, so it can write to the file presumably, and then in the time between the check and the attempt to actually access and write to the file, the state of the file has changed because some other process has locked that file. So to the degree this becomes undesirable, that becomes a bug in your software, and a developer can avoid that time of check to time of use problem by really checking the state of the resource it wants to access just in time. And I want to talk about the SafeCode standard, the last that's called out in the official exam syllabus. SafeCode was first published as Fundamental Practices for Secure Software Development. It's informed by existing models including OWASP, the Microsoft Software Development Lifecycle, and others. And it's designed to help the software industry adopt and use these best practices effectively. SafeCode itself covers topics like software design, secure coding practices, testing, validation, third-party risks, handling vulnerabilities. I will say SafeCode is certainly the least well-known of these standards. It was last updated in 2019, and in my opinion, fairly unlikely to appear on the CCSP exam, and certainly not in more than one question if it does. Now we'll just switch over to a browser and take a quick look at the SANS, OWASP, and SafeCode standards on the web so you'll know them when you see them. I'll have links in the PDF that you download with this course. Now here's SANS.org, the top 25 most dangerous software errors. You see a rank, you see the name, and in the middle here you have a link to read about the details. Again, the reading of the details here absolutely unnecessary if you've listened to my video here. And next we have the OWASP Cloud Native Application Security Top 10. So this one was last updated in April 2022. And then we have the OWASP Top 10 Web Application Security Lists. And you see here they even give you some visualization of how these risks have moved up and down the list over time. And then last on the list was SafeCode. So here is the fundamental practices for secure software development. This is a PDF you'll find from SafeCode. Again, at the end of this section in the PDF, you will find links to all of this additional reading if you like. So I want to shift gears and talk through some foundational concepts related to software configuration management and versioning that's called out in the syllabus. So let's talk about code repositories for a moment. This is where the source code and related artifacts like our libraries are stored. This is where our infrastructure as code is stored. So how do we handle source code securely? Well, we don't commit sensitive information. We're not keeping secrets on disk, for example. We protect access to our code repository, so we have authentication and authorization gating access to our code repositories. But protect access means we're only going to allow certain people to commit code to those repositories, to those repos as we call them. Signing your work. So typically code signing is assumed for your third-party commercial software vendors. If you look at any application in Microsoft Office, for example, you'll see that it is signed with a Microsoft certificate. Keep your development tools, your IDE, up to date. Most code repositories today use Git. Virtually everyone is using Git. It's the most widely used modern version control system. Created by Linus Torvalds, incidentally, the creator of Linux, also created Git. So IDE, if you're not familiar, is Integrated Development Environment, so that would be a tool like VS Code, which is the most common IDE today in use anywhere in the world. So let's move on to configuration and change management. So configuration management ensures that systems are configured similarly and configurations are known and documented. This is where baselining comes in. That ensures our systems are deployed with a common baseline or starting point. And imaging is a common baselining method, for example, in IaaS. But that baselining exercise can carry over to a number of technologies. We could baseline our configuration in a containerized environment, for example. Change management helps reduce outages or weaken security from unauthorized changes. So versioning is a way we can track our software lineage. Uses a labeling or a numbering system to track changes in updated software versions. Now, how folks do this differs. There are many approaches. What I often see is a major version, a minor version, and a patch version. So like 23.05.02, major, minor, patch. But all of these practices can help us prevent the shift and drift that results in security-related incidents and outages. So I want to dig into baselining just a bit further for a moment. So baselining is how we track how our systems are set up, not just our software, our applications, but our virtual infrastructure as well. That baseline is effectively a snapshot of a system or an application at a given point in time. It is our starting point. This process should also create artifacts that can be used to help understand our system configuration, and probably include some metadata. And we also want system and component level versioning. For example, if I have a VM that requires a Java library, I want to make sure that at a system level I know what that operating system is, but I also know what that Java library is. How we capture that depends on the type of underlying compute we're dealing with, the infrastructure, but at the end of the day, our applications depend on compute resources and other software components. There are many layers between the wire, between the network, and that application user interface that our end user is working in. And baselining is going to help us capture all of the details in between those 2 points. The last thing I'd like to talk to you about here in section 4.3 is the Software Bill of Materials, which is an emerging strategy and standard in tracking software versions. The SBOM lists all of the components in an application or a service, including open source libraries or proprietary code libraries for that matter. Think of it as a full inventory of the components of an application, and we really started seeing this get a lot of attention after Solarigate, where SolarWinds had a breach that reached all the way into their source code. But SBOM is mentioned briefly in the official study guide. It's not mentioned in the exam syllabus. You may see a question on there, I doubt it though, but do expect that SBOM is something you will see more and more of in the future. There are multiple standards coming together, and you'll see production of a software bill of materials integrated into pipelines as a future standard. It will be fully integrated into the CI/CD process. Now you know what it is, and that should be enough for exam day. So moving on to section 4.4, apply cloud software assurance and validation. So here we're going to talk about testing. We'll talk about functional versus non-functional testing, security testing methodologies like black box, white box, static and dynamic testing, and one you may not have heard of before, the interactive application security test. We'll talk about quality assurance and abuse case testing. Before we delve into testing methodologies, I want to talk for a moment on environment. So secure environments for development, testing, and staging before moving an application into production are absolutely necessary. And environments map to phases of application development, debugging, testing, and ultimately release. So the development environment is where an application is initially coded, often through multiple iterations. That's where Agile comes in. We iterate quickly through our sprints. Testing is where developers integrate all of their work into a single application. So we may have developers working independently in the development environment. They need to roll their code together in testing, where we can then integrate that work into a single application. Regression testing to ensure functionality as expected, for example, can happen here. Then we have the staging environment, where we ensure quality assurance before we roll out to production. QA happens here at minimum. QA may happen before this phase, but certainly in the staging environment we're going to see some QA happening, often taking the form of what we'd call UAT, or user acceptance testing, making sure that application functions exactly as we expect in production, or the changes to the application. Then finally production, where the application goes live and end users have the support of the IT team. So let's talk testing. So functional and non-functional testing. So functional testing determines if software meets functionality requirements defined earlier in the secure software development lifecycle. And it takes multiple forms, including integration testing that validates whether components work together, regression testing that validates whether bugs were reintroduced between versions, and user acceptance testing, which tests how users interact with and operate the software. Functional testing focuses on specific features and functionality. That's important. Now let's compare that to non-functional testing, which focuses on the quality of the software. It looks at software qualities like stability and performance. Methods here include load testing, stress testing, recovery testing, and volume test. It examines the way the system operates as a whole, not the specific functions. So continuing down the thought path here of functional and non-functional, let's talk about functional versus non-functional security requirements, and we're revisiting this concept from Domain 1. So what is the difference? Functional security requirements define a system or its components and specifies what it must do. It's captured in use cases defined at a component level. For example, application forms must protect against injection attacks, which we do with what? Input validation. Non-functional security requirements specify the system's quality, characteristics, or attributes. And again, it applies to the whole system. It's a system-level assertion. An example here would be security certifications, which are non-functional. So if we're looking to see that an application is HIPAA compliant, for example, or complies with PCI DSS, that's looking at the quality of that application as a whole. It's not a functional requirement. Again, we touched on this in Domain 1. I just wanted to refresh your memory and bring that forward here in context. So let's talk about static and dynamic testing. So static application security testing. It's analysis of computer software performed without actually executing programs. The tester has access to the underlying framework, design, and implementation. It requires source code access. And then there's dynamic application security testing, which is where a program communicates with a web application and it executes that application. It's exercising the application. The tester has no knowledge of the technologies or the frameworks that the application is built on. There's no requirement for source code access. So we say static testing tests the application from the inside out. Looking at the source code, dynamic application security testing tests the application from the outside in, exercising the application in live use, throwing unexpected input at forms, for example, to make sure that it protects against injection attacks. Next, we have white box testing, which is conducted with full access to and knowledge of systems, code, and environment. Static application testing is one example of white box testing. Remember, that required source code access. And then we have black box testing, which is conducted as an external attacker would access the code, the systems, and the environment. The tester has no knowledge of any of these elements at the outset of a test. So obviously no source code required there. Sometimes white box testing is called full knowledge testing, and black box testing is referred to as zero knowledge testing. Next, we have interactive application security testing, IAST, which analyzes code for vulnerabilities while it is being used. It focuses on real-time reporting to optimize testing and analysis processes. So unlike static and dynamic testing, IAST analyzes the internal functions of the application while it's running. So it's testing the application from the outside in, but analyzing those internal functions at the same time. It's often built into CI/CD automated release testing. And then we have software composition analysis, which is used to track the components of a software package or application. And it's of special concern for apps built with open source software components, because open source components often involve reusable code libraries. And SCA tools are going to identify flaws and vulnerabilities that are included in these components. They're going to ensure we're working with the latest versions. It's really automated and combines application security and patch management, so to speak. It's making sure that we're using the latest versions of the libraries and we're not exposing ourselves to vulnerabilities unnecessarily by not working on the latest version or potentially working with the latest version that has a known vulnerability. And then there's quality assurance, which is responsible for ensuring that the code delivered to the customer through the cloud environment is quality code, defect-free, and secure. From a process perspective, it's frequently a combination of automated and manual validation testing techniques. It typically involves reviews, testing, reporting, and other activities to complete the QA process. So it's going to be a combination of people and process. The goal of QA is to ensure software meets standards or requirements. Because DevSecOps preaches security is everyone's responsibility, the role of QA is significantly expanded in a DevOps or DevSecOps team, and it tends to be embedded throughout the development process because security is an element of quality. And in DevSecOps, where security is everyone's responsibility, we shift left and we start looking at security from the very beginning of the software development lifecycle. And QA should be involved in many testing activities, including load and performance test, stress testing, as well as vulnerability management. So QA testing is looking at functionality, performance, and security. So what is an abuse case? Well, an abuse case is a way to use a feature that was not expected by the implementer, allowing an attacker to influence the feature or outcome of use of the feature based on the attacker's action or input. It describes unintended and malicious use scenarios of the application, describing how an attacker could do this. And an abuse case test takes that abuse case and puts it into action. It focuses on using features in a way that weren't intended by the developer. It may exploit weaknesses or coding flaws from the perspective of multiple personas, a malicious user, abusive user, and even an unknowing user. It can help organizations to consider security features and controls needed for an application. In fact, OWASP provides an abuse case cheat sheet in their cheat sheet series at owasp.org that we've looked at earlier in this series. but testing generally focuses on documented abuse cases. And those test cases could come from a number of sources, including our outputs from threat modeling, where we're looking at the vulnerabilities of our services and the attack surface. That brings us to Section 4.5, Use Verified Software. Here we'll talk about securing application programming interfaces, APIs. We'll touch on supply chain management and vendor assessment traditionally versus in the cloud, third-party software management, and validated open source software. So by the by, if you're using the official study guide, these last two come from Chapter 5 of the official study guide. Beyond that, the entirety of Domain 4 is covered in Chapter 6 of the official study guide. So let's talk about APIs. We have SOAP and REST. So an API is a set of exposed interfaces that allow programmatic interaction between services. That means no user or human involved. SOAP is a standard communication protocol that uses XML. REST is an architectural model that uses HTTPS for web communications to offer API endpoints. And your security features from the CSP include API gateway functionality, authentication, IP filtering, throttling, quotas, data validation, generally offered through those PaaS services that I've mentioned in the past, in previous domains in this series. So you have API management in Azure, you have the API gateway offering in AWS. You also need to make sure that you have a plan for storage, distribution, and transmission of your API access keys. Those need to be maintained in a secure fashion, both at rest and when they're being transmitted between parties for whatever reason. So let's talk supply chain. Today, most services are delivered through a chain of multiple entities. A secure supply chain includes vendors who are secure, reliable, trustworthy, and reputable. Due diligence should be exercised in assessing vendor security posture, business practices, and reliability. This may include periodic attestation requiring vendors to confirm continued implementation of security practices. I can tell you firsthand this typically happens on an annual basis at least. We'll typically see an annual vendor survey from Microsoft as well as customers in regulated industries. And a vulnerable vendor in the supply chain puts not only the organization at risk, but potentially other members of the supply chain. So let's examine vendor assessment in our supply chain from a couple of perspectives. So traditional vendor evaluation would occur through a number of different options. So on-site assessment is an option, visiting the organization, interviewing personnel, and observing their operating habits. So in extremely sensitive scenarios or where human safety is involved, that's certainly an option we'd see exercised. Document exchange and review, investigating dataset and document exchange. Process and policy reviews, we request copies of their security policies, processes, and procedures to make sure that the security they attest is in place is actually in writing. And then third-party audit, having an independent auditor provide an unbiased review of an entity's security infrastructure. Now these are all options a CSP like AWS or Azure or Google might use to evaluate a vendor. Now in the cloud, companies with hundreds or thousands of customers, like our CSPs, cannot support direct vendor assessment. So we can't perform the same type of review of these major CSPs. Instead, we're going to review, audit, and certification reports provided by the CSP directly. These could include a third-party audit, a review of an independent auditor's unbiased review of an entity's security infrastructure, provided to us by the CSP. We could also review a SOC 2 Type 2 report. We could look at the ISO IEC 27001, 27017, and 018 reports to verify the efficacy of the CSP's physical and logical security controls. And as we saw in Domain 3, your major CSPs generally make these reports available to customers for review on demand. We went to one of the CSP portals and actually retrieved these reports. We did have to sign an NDA to get to that SOC 2 Type 2 report, but as a customer, that was very possible. But this is how we evaluate a cloud vendor like a CSP or a SaaS offering. Third-party software also adds additional risk to our organization. A third party may have limited access to your systems, but will often have direct access to some portion of your data. If you think about Office 365 applications storing our documents in SharePoint and OneDrive, that's absolutely true. Limited system access, but direct access to our data. Typical issues addressed in software vendor assessment would include where in the cloud is the software running? Is this on a well-known CSP, or does the provider use their own cloud service? That's going to give us some insight into reliability, or at least raise additional concerns potentially to go assess this vendor further. Is the data encrypted at rest and in transit, and what encryption technology is used? Not only are they encrypting the data, but have they made good decisions in terms of encryption algorithm selection? How is access management handled? Access management is going to be tied to our identity provider there. So really, what is the identity and access management system that service runs on? For example, with Office 365, we're talking about Azure Active Directory. With Google Cloud Platform, we're talking about Google's own identity platform. So identity as a service often makes us feel a bit better, a bit more comfortable. What event logging can you receive? We talked about the level of logging across different cloud deployment models, and we know we're going to have greater access to logs in areas where we have greater responsibility. So our log access is greater in IaaS than it is in PaaS, and it's greater in PaaS than it is in software as a service. And what auditing options exist? And we just talked about auditing in the cloud, and we know that even when we are working with a vendor that has many hundreds of thousands of customers and we can't audit directly, generally speaking, we're going to have access to their audit documentations and assertions in the form of SOC 2 Type 2 reports and the like. The focus here is on risk to data security. So let's talk open source software versus proprietary. Open source is one where the vendor makes the license freely available. They allow access to the source code, though they may ask for an optional donation in exchange for access to source code. There is no vendor support with open source, so you might pay a third-party company to support in a production environment. We definitely see this with certain flavors of Linux. Another example is one of the more popular open source firewalls, pfSense. Now, proprietary, on the other hand, tends to be more expensive, but tends to provide more and better protection and more functionality and support, albeit at a cost. So in the firewall example, there are many vendors in this space, including Cisco, Check Point, Palo Alto, Barracuda, and we don't get source code access in the case of proprietary either. So if we're using open source software, we want to use validated open source software. It must be validated in a business environment. So we have some risk when it comes to open source. And some argue that open source software is more secure because the source code is available for review. I would say that we can definitively prove through evidence that is not guaranteed. Now, adequate validation testing through sandbox testing, vulnerability scans, third-party verifications all reduce our risk, but more visibility into a problem can result in better outcomes, but the transparency is not itself a guarantee of security. And I can cite two great examples here. And that would be open source projects like OpenSSL and Apache, which have contained serious vulnerabilities in the past. Just because everyone's watching doesn't mean every security issue is identified and remediated. And that brings us to Section 4.6, Comprehend the Specifics of Cloud Application Architecture. In this section, we'll cover supplemental security components. We're going to talk about flavors of firewalls or gateways in the cloud. We'll talk about cryptography, sandboxing, as well as application virtualization and orchestration. We'll start with supplemental security components, which are called out here in the syllabus, beginning with a web app firewall, often abbreviated as WAF, which protects web applications by filtering and monitoring HTTP traffic between a web app and the internet. It typically protects web applications from common attacks like cross-site scripting, cross-site request forgery, SQL injection, attacks on the OWASP top 10 quite often. And you'll often find these WAFs include default OWASP core rule sets. And this is fairly common in your CSPs. We'll take a look at a WAF here in just a moment. And then there's the XML firewall, which is used to protect services that rely on XML-based interfaces, including some web apps. It provides request validation and filtering, rate limiting, and traffic flow management. I think the main thing you need to remember here is that it services XML traffic, usually implemented as a proxy. Then we have database activity monitoring, abbreviated as DAM. That's the associated acronym. This combines network data and database audit info in real time to analyze database activity for unwanted, anomalous, and unexpected behavior. It monitors application activity, privileged access, and it detects attacks through behavioral analysis. So there's some intelligence to this tooling. And most of your CSPs offer some form of DAM tooling as a service that you can enable. And finally, we have the API Gateway, which provides traffic monitoring for your application services exposed as API endpoints. It provides authentication and key validation services that control access to your APIs. In the cloud, your CSPs, Amazon offers the API Gateway, Azure offers the API Management service. Both of those are PaaS offerings that I've alluded to previously in the series as providing a number of services to secure your APIs. Okay, so I'd like to do some quick show and tell here. This is a good opportunity. We're going to look at a web app firewall in a CSP and examine the OWASP core rule sets. We'll just switch over to a browser here, and I'll start at the OWASP.org website. I wanted to point you to the OWASP core rule sets here. It's just a set of generic attack detection rules for use with compatible web application firewalls. So it gives you a broad range of protection against many of those attacks defined in the OWASP Top 10. Injection attacks, cross-site scripting, cross-site request forgery, just to name some of those more popular. Now I will switch over to my portal here. So I'm at portal.azure.com looking at the Microsoft Azure portal, and I've drilled down to a web application firewall instance. And if I look at managed rules, I'll see here that by default they have implemented the OWASP 3.2 core rule sets. And the way it tends to work in the Microsoft scenario anyway is they support the last 3 sets of the OWASP core rule sets. It's going to vary by CSP, but the point is you can deploy a firewall, and by default it's going to have these built-in web protections. You can run your web traffic through here and feel pretty good about your security posture right out of the gate. So just a very quick look. But if you go down the list here, you'll see the rules in the set are numbered, so you can go find some additional explanation for those rules out on the OWASP website if you're interested. But for the exam, just know that's really one of the key value propositions of a web app firewall. And finishing up our discussion on firewalls, obviously anytime we're in an internet-connected environment, a firewall is important for filtering incoming traffic in a perimeter network. But that web app firewall, the WAF, is one that you're going to find is very common. It's really the most popular firewall generally speaking, and there are a couple of reasons for that. One is cost. It meets a common need, it's easy to configure, it comes with those default OWASP core rule sets, and it's less expensive than the more function-rich next generation firewalls and secure web gateway firewalls. Now we will see those more feature-rich firewalls implemented as well, but for other reasons. Now, the need for network segmentation, for example, should be supported with appropriate traffic filtering and restriction with the firewall that's most appropriate for the use case. And when we get into heavier traffic filtering and cross-cloud scenarios or hybrid scenarios, that's where you're going to step up to a next-generation firewall. It'll have advanced functionality, centralized policy capabilities, real-time threat intel connected to that device. In fact, real-time threat intelligence is part of what makes a next-generation firewall a next-generation firewall. And that firewall can filter traffic between our virtual networks and the internet, or our virtual networks and our corporate network. The common theme there is segmentation. When we think about zero-trust network architecture, it focuses on micro-segmentation. And you'll find your firewall functionality maps to different layers in the OSI model. So we have a 7-layer OSI model. A network firewall works at layer 3 of the OSI, stateful packet inspection at layer 3 and 4, and many of your cloud firewalls, like the web app firewalls, work at layer 7 of the OSI model, which is the application layer. Now, cryptography is mentioned in this section of Domain 4, and it really touches on 3 areas: data at rest, data in motion, and key management. And I've talked about key management endlessly throughout the series, so I want to just say a couple of words on data at rest and data in motion. So data at rest. We need to encrypt our storage accounts, and your CSP storage providers usually protect data at rest at the account level by automatically encrypting before persisting it to manage disks, blob storage, file, or queue storage. But you have a default layer of encryption. What you'll find sometimes is they offer an additional layer of encryption, what we call double encryption. So the customer can hold the keys. It enables crypto shredding, secure deletion in an environment where you don't own the physical storage medium. We talked about this earlier in the series. And then full disk encryption. This is BitLocker or dmcrypt on the Linux platform. If you've ever worked in the Windows ecosystem, a Windows desktop, you're probably familiar with BitLocker. You'll find CSPs offer this capability in their IaaS model when you're working with VMs. And then there's transparent data encryption for SQL databases and data warehouses that give us protection against the threat of malicious activity with real-time encryption and decryption of the database, backups, and the transaction log files at rest without requiring app changes. These features generally include a customer managed key option. And I use that acronym SQL generically here. You'll find transparent data encryption is available on more than just the Microsoft SQL platform as you look at MySQL and PostgreSQL. How do we encrypt data in motion? Well, there are a couple of most common methods. The first being transport layer security over HTTP, so HTTPS. And in hybrid cloud scenarios and cross-cloud connectivity, we often see traffic tunneled over a VPN connection. You'll sometimes hear TLS referred to as SSL. The terms are used interchangeably, but TLS replaced SSL a long time ago. Shifting gears, let's talk about sandboxing for a moment, placing systems or code into an isolated, secured environment where testing can be performed. Cloud sandboxing architectures often create independent, ephemeral environments for testing and serving multiple purposes. We can enable patch and test scenarios, ensuring a system is secure before putting it into a production environment. It also facilitates investigating dangerous malware. And you'll see that in a couple of scenarios. In email protection, you'll see email attachments and URLs delivered in messages detonated in a sandbox before they are delivered to the recipient. And you'll also find some of your XDR functionality, your desktop protections, your endpoint protections that will have some sort of sandboxing scenario where you can isolate a potentially infected node and investigate before restoring full network connectivity. And at the end of the day, sandboxes provide an environment for evaluating the security of code without impacting other systems as well. So we'll round out section 4.6 with a talk about app virtualization and orchestration. So let's start with a quick refresher on containerization. And I'm thinking about Docker and Kubernetes here, where one of your key value propositions is containers do not have their own OS, so we get greater density in our virtualization infrastructure. And we can use containerization in some cases to isolate existing applications developed to run in a VM with a dedicated operating system. Containerization can fool an application basically into thinking it has its own kernel when in fact it doesn't. It's sharing. So in terms of hypervisors, you remember we have the Type 1 hypervisor, which is the bare metal hypervisor, VMware ESXi, Microsoft Hyper-V, what you'll generally be dealing with in a CSP scenario. And our VM runs atop that hypervisor. Each VM has its own OS kernel and memory, which results in more overhead. With a container host, which is a virtual machine typically, we have containers running in that single operating system. So the containers are isolated, but they share an OS kernel, as well as binaries and libraries where possible. So we're getting greater density, essentially. So core components in a container platform, we have the orchestration or scheduling controller. network and storage, a container host, container images, which are functionally parallel to what we'd see with a VM template, and your container registry, where we store our container images. The isolation is logical, isolating processes, compute, storage, network, secrets, and management plane. But Kubernetes is a container orchestration platform for scheduling and automating the deployment, management, and scaling of containerized applications. And all your major CSPs have a managed Kubernetes flavor. Your container hosts are the cloud-based virtual machines. This is where the containers run. Most of your CSPs offer that hosted service. It's a PaaS offering, and you only pay for the agent nodes within your cluster. You don't pay for the Kubernetes management cluster. That's why it's a managed Kubernetes environment. And your major CSPs generally offer a monitoring solution that will identify at least some potential security concerns in the environment. And those offerings are AKS in the Microsoft world, EKS on the AWS platform, and GKE in Google Cloud Platform. And finishing out 4.6, we have cloud orchestration, which allows a customer to manage their cloud resources centrally in an efficient and cost-effective manner. The intent of reducing effort, cost, and complexity. And this is going to be very important in a multi-cloud environment. And we're seeing more customers move to a multi-cloud stance to reduce their risk exposure. And management of the complexity of corporate cloud needs really only increases over time as more and more workloads move to the cloud and we see more and more multi-cloud scenarios. But it allows the automation of workflows, the management of accounts, in addition to the deployment of cloud and containerized applications. And it implements automation in a way that manages cost and enforces corporate policy in and across clouds. Your major CSPs offer orchestration tools that work on their platform, and the third parties offer multi-cloud orchestration solutions. In fact, your CSPs will offer orchestration capabilities for customers as well as their service partners who manage environments for multiple customers. And that brings us to 4.7, design appropriate identity and access management solutions. So here we'll touch again on federated identity, identity providers, single sign-on, multi-factor authentication, cloud access security brokers or CASB, and secrets management. So definitely topics we've seen before in the series. There'll be a bit of refresher here, but I'm going to interlace this with some new details. Let's start with federation. So federation is a collection of domains that have established trust. The level of trust may vary, but it typically includes authentication and almost always includes authorization. In fact, it has always included both in the scenarios I've been exposed to, and it often includes a number of organizations that have established trust for shared access to a set of resources. For example, you can federate your on-premises environment with Azure Active Directory and use this federation for authentication and authorization. This sign-in method ensures that all user authentication occurs on premises, which allows administrators to implement more rigorous levels of access control. For example, historically we'd use federation when certificate authentication or key fob or a card-based token was desired. Now, some of this capability, certificate authentication in particular, is possible with some identity as a service providers, cloud identity providers, but that was one of the core value propositions of federation when we wanted authentication and authorization to take place on premises and we wanted to implement more rigorous methods. Now let's look at a federation scenario I think will resonate for you. So we have a website that authenticates with identity provider A. Let's say that's Azure Active Directory, the identity provider of Office 365. And we have a user that authenticates with identity provider B. Let's say that's their Twitter account. So we configure federation. So identity provider A trusts identity provider B. And identity provider B then has shared access. And this may be cloud or on-premises. And trust is not always bidirectional. But this sort of support for federation is quite common in your identity as a service providers. In fact, earlier in the series I showed you how easy it was to add identity providers like Facebook and Google and others to Azure Active Directory. It has some built-in support for social identities. And on that note, let's talk about identity providers. So identity providers create, maintain, and manage identity information while providing authentication services to applications. For example, Azure Active Directory is the identity provider for Office 365. Some of your other identity as a service options include Okta, Duo, OneLogin. And on that topic of social identity providers I mentioned, social identity providers that support OAuth, like Google, Facebook, and Apple, are common in federation scenarios. Think about all the cloud apps that you subscribe to where you can log in with your Google account or your Microsoft account or your Facebook account. And single sign-on is a concept where a user doesn't have to log in to every application they use. They essentially sign in once and they can use that credential for multiple applications. Single sign-on based authentication systems are sometimes called modern authentication. And this is a very common user experience issue in enterprise desktop scenarios. We have to create a user experience so the user can log in one time and more or less have access to all the applications installed on their desktop, whether those are authenticating locally or to an Active Directory domain or to a cloud identity provider like Azure Active Directory for your Office suite. Multi-factor authentication. So let's talk about MFA attack prevention, for example. So we know multi-factor authentication are two or more methods combining something you know, like a PIN or a password, with something you have, like a trusted device, something you are, so a biometric authentication method like fingerprints on most of your mobile devices out there, and potentially facial recognition if you're using a fancier smartphone. But MFA is a preventative security control for multiple attacks. So MFA can prevent phishing attacks, spear phishing, keyloggers, credential stuffing, brute force and reverse brute force attacks, man-in-the-middle attacks, in large part because we're tying that second factor back to something the user has or something that they are. And most of your data loss, your data breaches, happen as a result of credential theft, and all of these attacks are used in credential theft. In fact, in talking to some of Microsoft's DART organization, the folks who go out and help customers who have been breached, one of those consultants told me that a lack of MFA is a causal factor in almost every security breach they've gone out to clean up. And to dig a little deeper on a concept we'd mentioned briefly before, the CASB, the Cloud Access Security Broker, which enforces the company's data security policies between on-premises and the cloud, really anywhere a user is trying to access and share and store company data. It can detect and optionally prevent data access with unauthorized apps and data storage in unauthorized locations. So if, for example, we wanted to prevent a user from accessing a Word document or a text document with some third-party generic app, we could stop that. If we wanted to prevent storage in a third-party cloud repository like Box or Dropbox, we could implement protections to prevent that. It combines the ability to control use of services with data loss prevention and threat management features. It's often used in enterprise scenarios where high levels of control and assurance in cloud usage are necessary. Now, there are on-premises, hybrid, and cloud-hosted models of CASB. I really see cloud-hosted CASBs everywhere I look these days. And just a quick reminder on secrets management. Remember, CSPs offer a cloud service for centralized, secure storage and access for application secrets, a vault solution. A secret's anything you want to control access to, your API keys, passwords, certificates, tokens, cryptographic keys. The service will almost always offer programmatic access via API to support DevOps and continuous integration and continuous deployment, your CI/CD pipeline. Access control is generally offered at the Vault instance level as well as to the secrets stored within the Vault. Your CI/CD pipelines should leverage centralized storage of secrets rather than hard-coded values or storage on disks. And Microsoft AWS and Google Cloud Platform all have a vault for storing your secrets centrally. And congratulations, you have reached the end of Domain 4 of the CCSP Exam Cram series. I hope you're getting value from the series. If you have questions, you can drop them in the comments below the video. Reach out to me directly on LinkedIn through the chat feature over there. I'll look forward to seeing you in Domain 5. So until next time, take care and stay safe.